Hi everyone! Our group's material of interest was lead perovskites and their applications in LEDs. Perovskites are crystals. They are naturally occurring in the environment, and they were first discovered in Russia in 1839 by a German scientist Gustav Rose in honor of a famous Russian mineralogist, Perovsky. It wasn't until 1950s when they started being incorporated into fuel cells, glass ceramic particles, catalysts, gas sensors, heating elements, and superconducting devices. Then in 1980, their photoelectric properties started being recognized as valuable, so they started applying perovskites into light-emitting diodes, or LEDs. Current challenge of lead perovskites is that they contain lead, as they are toxic and expensive. Also, current methods are still not efficient for large-scale manufacturing, so researchers are studying to lower or replace the lead content and be able to produce crystals of perovskites at a larger scale. All perovskites take the general formula of A1M1X3, where A is an organic or an inorganic cation of +1 charge. M is also a cation with +2 charge, and X is a halide. Since we are dealing with lead perovskites, the M cation for this presentation is always going to be lead 2+. The crystal lattice may be cubic, tetragonal, or orthorhombic depending on the temperature and the identities of the A cation and the halide. Thus, lattice parameters vary across different applications. The lattice is assembled with halides arranged in a primitive cubic structure in cubic close-pack arrangement, and the cations occupy octahedral holes. This arrangement is such that the s and p orbitals of lead and halides overlap, such that electronic transitions between these overlapping orbitals are allowed within the UV-Vis region. Methods to synthesize crystals of perovskites are still being developed and improved. I am going to share with you a method that was used in a study in 2020 to make cesium lead bromide. They used a process called LARP, which stands for Ligand-Assisted Reprecipitation. This process occurs in 3 steps: preparation, precipitation, and separation. First, salts of cesium bromide and lead bromide were dissolved in dimethylformamide, or DMF, which is a polar solvent. The solution was prepared with oleic acid and octylamine, which are ligands that ensure a stable colloidal dispersion of particles. Then the resulting solution is poured into a vigorously stirring ethyl acetate, a solvent in which the salts have poor solubility. The sudden drop in solubility causes rapid precipitation of the salts as nanocrystals. Finally, the mixture is centrifuged to separate the crystals from the ligands. As an optional step, if you want to change the halide composition of your crystals, they can simply be ultrasonicated in an aqueous lead or cesium halide solution. Researchers are trying to improve their methods by changing the solvents, ligands, and their ratios. This particular method seems to work better than previous methods. It afforded 290% higher yield than the traditional method that used toluene, and better stability was observed with this set and ratio of solvents and ligands. An additional advantage of this method is that it can be scaled up without significant changes to the procedure. As I've mentioned before, the overlap of lead and halide orbitals give rise to the photoelectronic response in perovskite crystal. This means that the wavelength of luminescence can be controlled easily by tuning of the halide composition. The figure on the left shows how different halide compositions show emission spectrums at different wavelengths of light. Because the atoms are fixed in crystalline structure, the atoms are less probable to lose energy to collisions. This results in high color purity and high thermal stability that then results in enhanced photoluminescence quantum yield, short exciton diffuse length, and narrow emission bandwidth. Because perovskites are essentially salts, they exhibit some degree of electrical conductivity and can be air or moisture sensitive. These properties can be applied in display light sources such as lasers and LEDs, photodetectors, and solar cells. For LED applications, when an electric current is passed through the semiconducting perovskite crystal, excited electrons and holes are produced, and the relaxation of these electrons to holes emit light. In organometallic halide perovskite quantum dots, or OHP quantum dots, initial applications showed poor performance and low stability due to defects. Recall that the synthesis of perovskites is simply crashing crystals out of solution. It's hard to expect obtaining something uniform through such an untamed of a process. Interactions with air and moisture can also produce defects as well. These challenges are being addressed by stacking uniform films of OHP quantum dots and improving stability by varying ligands during synthesis and packaging the final product to protect the crystals. We'll get to talk more about packaging shortly in the next slide. For precise tuning of the LED device, careful characterization of the crystal products is necessary. We can use SAED to confirm if the crystal is single crystal in nature. If so, the diffraction pattern will show up as dots instead of rings. We can use TEM images to determine the crystal size and get some insight into the compositions of the crystals. For example, in CS-PbBr3, the relative weight percent of Pb, which is the heaviest out of the three atoms, is greater than CS4-PbBr6, so they will appear as darker images in the TEM image. We can use XRD to find the number of crystal phases present and confirm their lattice structure and lattice parameters. For example, in the XRD spectrum shown, we can see that the additions of Miller indices are multiples of 2. So we know that the crystals are arranged in body-centered cubic structure. As an interesting aside, the XRD shows a comparison between the red line, which is a spectrum of a perovskite crystal by itself, and the green line, which is a spectrum of a perovskite coated with a thin layer of zinc bromide. This packaging of the crystal with zinc bromide salt minimizes the crystal's contact with air to reduce Schottky defects, but it doesn't affect the crystal lattice structure or the photoelectronic properties of the crystals. So, this packaging idea is where current studies are going to address the air moisture sensitivity problem of perovskites, which I think is really cool. We went over how photoelectronic properties of perovskites are useful in applications as light sources, and how the color of the LEDs can change by changing the crystal compositions. The defects in the crystals can be reduced with zinc bromide deposition on the surface, leading to better optical performance by preventing Schottky defects. And the methods are constantly improving to produce perovskite crystals with thermal stability and efficiency that are more attractive compared to classic LEDs. I hope my delivery of these ideas to you was effective and informative. I can't wait to see what the rest of you have prepared. Thank you.